All right, so this is Access Reality. I'm Ali Kadili. We're honored today to have Dr. Amanda Hendrix with us. She's a senior scientist at the Planetary Science Institute, co-investigator of the Cassini and Galileo projects, as well as the principal investigator at the Hubble Space Telescope observation programs. Her main interests are moon and smaller objects in our solar system and using ultraviolet spectroscopy to study their surfaces. She co-authored the book Beyond Earth, Our Path to a New Home in the Planets. So welcome, Dr. Hendrix. Thank you for being here today.
Thank you for having me.
All right. So I found out that there's an asteroid named after you, the 6813 Amanda Hendrix.
Yes, there is.
That's awesome. Talk about checking off items off a bucket list.
I know.
How does someone get a celestial body named after them?
Well, that was a surprise, a pleasant surprise. I think that happened a couple of years ago. Evidently, you can nominate to a board who goes off and looks at all the newly discovered objects, and you can go in and recommend names for these objects. And I don't exactly know what the process is. I've never done it, but you can recommend names. And often, evidently, it's done to kind of recognize people's work or recognize a notable person in the science community. So I was really pleased and honored to have that distinction.
All right. Is it an asteroid in the Kuiper Belt or?
No, it's in the main belt. It might actually be an NEA, like a near Earth asteroid, but it's not way out in the Kuiper Belt.
Are you following it closely like it's your baby?
Not really. Maybe I should more often. I should probably know more about it.
It has your name. You have more in common with it than a lot of other things. All right, great. So your book mainly argues for the choice of Saturn's moon Titan as the best choice for human settlement in our solar system. So do you think your book title should be changed to A Path to a New Home in the Moons rather than the planets?
Right. Well, what we wanted to do with the book was come up with a scenario where, we don't necessarily argue that Titan is the best place to send humans, first, but we wanted to come up with a place in the solar system that is fairly realistic if we get to the point where we want to set up a sustainable settlement in the solar system. So a permanent settlement. And when we kind of considered all of the planets and a lot of the moons in the solar system to try to decide, well, what would be the best place for a permanent and sustainable settlement, we came up with Titan. And the reason that we chose Titan was because it's quite Earth-like in a lot of ways. And it's much more suitable to having humans live there for the long term, because one of the most kind of show-stopping aspects to deep space flight for humans is the radiation problem. And Titan has a thick atmosphere, mostly of nitrogen, and so that atmosphere acts as kind of a natural shield to much, or if not all, of the damaging radiation out there.
It actually has a thicker atmosphere than Earth, doesn't it?
Yes, it has. It's about as 5 times denser than Earth's atmosphere. And in terms of surface pressure, if you were standing on Titan, you'd feel about 1.5 times the amount of pressure that you feel from the atmosphere here on Earth. So it's not like super heavy. You wouldn't feel weighed down like if you were standing on Venus or something like that. So it's kind of a really, in that way, it's very kind of Earth-like.
Yeah. So now do you think it gets some radiation also from Saturn, maybe Jupiter also, that we wouldn't be exposed to here? So would that offset some of the advantage of it having a thicker atmosphere?
Well, actually, that's a good question, because Titan does, for most of its 16-day orbit, it is in Saturn's large magnetosphere. But those particles, they're, on the range of, a few keV up to, plenty of MeV. But most of the really energetic stuff is much closer in the radiation belts, not close to Titan. So the energies of Saturn's magnetospheric particles that are hitting the top of the Titan atmosphere do not make it down to the surface of Titan. They get absorbed. They do a lot of important chemistry, actually, to the atmospheric constituents. And Jupiter's radiation environment, I should say, since you asked about that, is fully contained inside its magnetosphere. So that doesn't make it out to Saturn at all.
Oh, but it makes it out to Jupiter's moons, though, doesn't it?
Sure. Yes.
Yeah.
For sure.
Okay. Has the radiation from the surface of Titan, from that perspective, been measured, or are we just kind of extrapolating?
We're kind of using models to know, get the penetration depth of different particles and what we know about them and how they get absorbed in different environments. But we will learn more, I expect, from future missions to Titan that make it to the surface.
Yeah. Is everything we know about Titan's physical condition, does that come from the Cassini mission?
Most of it comes from Cassini. Now there's plenty of, first we learned about Titan, some of the first measurements were from Voyager, from the flyby back in the early 80s. And that's when we first kind of knew that, well, Titan has got a really thick, dense atmosphere. So thick and dense that we can't actually see down to the surface. And so that kind of helped us to understand, well, when we're going to send the Cassini orbiter to the Saturn system, what instruments do we need to carry on board in order to probe through that thick atmosphere and see what the surface looks like? We can't just use visible wavelength cameras because our eyes cannot see through the thick atmosphere. It's too absorbing. So that's one of the reasons why, that's the reason actually, that Cassini carried a radar, because those wavelengths can just probe right through that atmosphere. And even some of the longer infrared wavelengths definitely make it through. And so we can basically make maps of the surface using infrared wavelengths, look at some of the surface composition using infrared, and then definitely make radar maps of the surface. So, and then also, that's mainly how we learned about Titan. But also, of course, the Cassini-Huygens mission carried along with it the Huygens probe. And this was a small probe that was released shortly after we arrived in the Saturn system. This was back in late 2004. The probe was released from the main orbiter spacecraft, and it flew through the Titan atmosphere and made measurements all the way down. Atmospheric measurements about the temperature and composition and wind speeds and so forth, and then it landed on the surface. It had a parachute to help slow it down through the atmosphere, landed on the surface, and that's really important, because now we actually have in situ measurements of at least that part of Titan's surface and that part of the atmosphere to understand it and to link it to the orbital observations. Interestingly, it had been proposed that Titan's surface, due to the likely temperatures and the likely makeup of the atmosphere, it was suggested that Titan would have an ocean covering its entire surface. It would be a hydrocarbon ocean because it's cold temperatures out there, and hydrocarbons like methane and ethane are liquid at those temperatures. And so that Huygens probe was designed so that it could survive whether it landed on a solid surface or whether it landed in a liquid ocean. And as a matter of fact, it landed on a solid surface, although there are some indications that it was a little bit damp, actually, where it landed. So that's how we know a lot about what Titan looks like.
That's awesome. And is that probe still functioning? Is it still?
No, it's not. No. It was not designed to last for very long. It had a battery on it. It sent its data up to the Cassini spacecraft as it flew over, and then died some tens of minutes later, as expected. So that was fine.
Was there any thought or ideas given to possibly sending a rover mission to Titan?
Yes, there's a lot of ideas for which next missions to send to Titan. And there is a NASA mission that is selected that's going to go. It's going to launch, I believe, in 2026. It's called Dragonfly. And it's not a rover. It's even more exciting than a rover. It's a quadcopter, or it's a robotic kind of rotor craft. And it's going to go to Titan, and it can land on the surface, make measurements, and then it's got, basically it acts like a helicopter. It utilizes the dense atmosphere to fly to different locations. And so that's going to be really exciting and important to help us understand Titan's chemistry in a few different places, and also potentially even its habitability, because there's a lot of organics on the surface, and maybe even some liquid water in some places on the surface. And so those two together might tell us something about habitable conditions on Titan or at the near surface.
Now, you said visually from outside, it's just a thick haze because of the atmosphere. And I've seen photos where it's either like an orange peachy color or sometimes green. Which one do you think it is?
It's generally thought of to be quite orangey in color. And that's real. That's because of the chemistry. And it's mainly because of the hydrocarbon chemistry. The surface is mainly nitrogen, N2, but it's got about 1% or so of methane, CH4, and then trace amounts of a bunch of other stuff too. But it's mainly that hydrocarbon chemistry with solar UV photons coming in, Saturn's magnetospheric particles that we talked about coming in, hitting the top of the atmosphere and doing chemistry on those atmospheric constituents. And what results is haze particles. So you make kind of aerosols from that chemistry. And there's haze layers in the atmosphere, just like a smoggy day here on Earth, which is, again, why we can't see down to the surface with our eyes. And those aerosols, the haze particles, actually are made up of complex organics. And they end up getting heavier and heavier as they get down closer to the surface, and they end up settling down on the surface. And they're an orangey, kind of browny orangey material. They're actually referred to as tholins, which can be made in the lab by irradiating carbon-based gases like CO2 or methane with UV or plasma irradiation. And you can make this tholin gunk. It's an organic substance, and it's usually kind of gunky, like almost like a tarish type of substance in the lab, which might be what Titan's surface is like if it's covered with this gunk that's settling down out of the atmosphere. Although we know also from Cassini that there are dunes on the surface of Titan. At particular latitudes, there are dune fields. So at least in past periods, there has been enough wind at those latitudes, and the makeup of the particles on the surface, the grains on the surface, is such that they can be lofted by those winds and moved into dune fields. So it must be quite like they're on the scale of what we have for dune fields here on Earth. So it must be quite a similar process. And so that tells us something about what must happen to the tholin material that settles down out of the atmosphere, and how it must evolve if it can be produced into grains that can be lofted by winds and moved around into dune fields.
Yeah, so generally the geography, topography of what Saturn looks like, what Titan looks like on the surface is the closest thing to Earth from everything else in our solar system. Is that correct?
Yes. I don't think there's any denying that. I always say Titan is the most Earth-like place in the solar system other than the Earth. It has, we talked about the dunes that are quite like Earth dune fields. It's got the atmosphere, okay, which is only a little thicker than ours. And it has weather as a result of the atmosphere. We know that there is some wind. Let me just say a little bit about the wind, because we have the dune fields, so we know that there must be some wind to create the dune fields, although there have been other processes proposed to create them. But we also, there's the the measurements made by the Huygens probe measured wind speeds and directions as it was coming down. It measured, relatively high wind speeds up at altitude and then not so much wind down closer to the surface. I'll get back to wind in a second. Another thing that makes Titan very Earth-like is that there's liquid lakes on the surface. And again, that's the only place in the solar system other than Earth where there's stable liquids on the surface. And these lakes, again, because it's cold there, it's about 95 Kelvin or about minus 290 Fahrenheit. So it's quite cold, but that is the temperature that liquid hydrocarbons are liquid at. So these lakes and seas are made of methane and ethane, and they're stable, and they're very Earth-like looking. As a matter of fact, they were presumed to be lakes from from radar maps of the surface, just because they look so lake-like. They look a lot like lakes that we have here on Earth. But of course, it's just a radar map. It's just a radar image that we're looking at. So we don't have a smoking gun. But the smoking gun did come from later measurements from the Cassini-VIMS instrument, which is the visible and infrared mapping spectrometer. And it measured actually something that can only come from liquid, which is a glint of sunlight from one of the lakes. And this has been done a few times now, but that first time, everybody said, oh, that's a smoking gun. Those are definitely liquid lakes because we saw the glint of sunlight, which can only happen if that's actually a liquid surface there. But anyway, so there have been a lot of studies done to try to look for waves and wind-produced waves on those lakes, and try to derive wind speeds from any waves that are seen. And it's been hard because there's very few waves seen. And so we're probably talking like a meter per second wind speeds at the surface. But again, much higher than that up at altitude. Currently, it could be that things evolve with time, maybe season, and there have been windier epochs in the past. But anyway, there's also weather on Titan, making it Earth-like. We know that there's rain, that we have measured with Cassini evidence of rain on the surface. So right when we would expect it to be rainy, like in the springtime, northern springtime, an observation was made of a surface that was visibly darker than it had been the last time we had gone by. And then later on, it kind of brightened up like it had dried out a little bit. I should mention, speaking of springtime, that when Cassini arrived at Saturn, and Saturn's got about a 30-year orbital period. So it's about a 30 Earth year. So when we arrived in July of 2004, it was summer in the south. And then by the time we left 13 years later, it was almost a whole half of a year later. So it was summer in the north. And so that was really valuable to be able to measure seasonal variations on the planet and in the whole system, including on Titan.
Great, so it has seasons too.
Yeah.
Yeah. Now
So very Earth-like, very Earth-like.
Mm-hmm. And you mentioned the postulation by some that there might be some liquid water on some places, but do we know for a fact that there's ice, water?
Okay, we do know for a fact that there's ice. And the reason that we know that is because there's a lot of water in the frozen state out in the outer solar system. And all of Saturn's moons are composed primarily of water ice, and we know that. We do have some, and so Titan is no different. It's composed mainly of water ice. It's got rock in the interior. It's just that the surface is covered by organic material. And so depending on how thick that organic coating might be, you can imagine that water ice patches can be relatively easily exposed. And there have even been some hints of detections of water ice spectral signatures from place to place on the surface of Titan. So it's very cold. So we don't expect liquid water to be stable at the surface. I think I mentioned already, it's 95 Kelvin. So all the water is frozen, but one can imagine that if, for instance, there were an impact, like a meteoroid came in and hit the surface, created an impact that brings and generates a lot of heat. And so there would be some local liquid melting of the water. And by the way, speaking of meteoroid impacts, there's very few craters on Titan. And that's because it's got the thick atmosphere. So it actually, you know, you've got to be a pretty big impactor if you're going to come in and make a crater on Titan.
Could it be that that's because Saturn is protecting it? It takes most of the brunt, whereas someone like Earth, we're just, you know, there's no other big body with a gravity that's kind of taken most of the heat, so to speak.
Well, it's probably actually because of the atmosphere again. Because, you know, there's probably impactors coming in. Maybe a lot of them head more closer into Saturn, it being more gravity. But most of these things are going to be pretty small, and they're just going to burn up in the atmosphere, just like here on Earth when we see shooting stars.
I see. So in terms of conditions for, you know, for humans settling on Titan, given that the radiation issue is kind of solved on its own, probably other than the lack of oxygen in the air and the gravity issue, which we can talk about later, would you say the biggest issue is the temperature? Because if it was warmer, then we'd have liquid water, and all these hydrocarbons would be gases rather than liquid, which, I mean, they could be utilized either way for energy, either way in any form. But would you agree that that's mainly the biggest issue or problem, so to speak, with Titan?
Yes. I think there's two big things. The temperature is one for sure. I mean, it is cold. Practically any place we go in the solar system where humans are going to go, it's going to be cold, and they're going to have to deal with it, right? Usually the way I think about it on Titan is that, you know, there's so many resources there to produce energy that keeping warm is not going to be a problem. There's plenty of H2O, frozen, that we can use, that can be utilized, that can be resourced to make water for humans, and also to do electrolysis on to make oxygen. Because as you pointed out, there's no oxygen in the atmosphere. So, normally when we think about making energy out of hydrocarbons, we're talking about combustion, say, of the methane. And it turns out that when you source the water, melt it, do hydrolysis to make the O2, and then do the combustion with the CH4, that actually does not end up being a positive outcome in terms of energy. So if you wanted to use combustion of hydrocarbons as an energy source, you might want to think about setting up maybe like a nuclear site to take care of all the electrolysis, and then just have a combustion station to make energy out of the hydrocarbons. There's other you could do hydrogenation of the acetylene. That produces energy, actually. That has been proposed. There's also hydrogenation of the nitrogen in the atmosphere. Doesn't look like that creates a ton of energy, but it does come out on the positive side. So those are all chemical energy options that might be used, so that humans can make energy to make heat in the habitats and do whatever else they might need to do. There's even other options too. Given that there are lakes on the surface, sometimes here on Earth we use lakes and build a dam and use hydropower. Maybe on Titan we'd call it methano power. But I've done some calculations. One of the big seas on Titan is called Kraken Mare. And if you can imagine, if the topography is right, because generally you're talking about building a dam and dropping all the liquid over a certain height and producing power that way. If you consider how big Kraken Mare is with the volume of methane, liquid methane, it probably is in there. It's bigger than Lake Superior, and the amount of power that you produce by creating methanopower from Kraken Mare is, you know, hundreds or thousands of times more what you could create from Lake Superior on Earth. So that's potentially an option. And then, of course, there's wind power, because as we talked about, there's not that much wind, at least right now, down close to the surface, but you can consider like airborne wind stations, maybe tethered to the surface, and you can create some serious power that way. And I believe people here on Earth are talking about tethered power, airborne power stations here on Earth. And then another pretty straightforward energy option is solar power, which some people sort of say, oh, there's 100 times less solar flux making it out to Saturn, right? Because it's 9 times farther from the sun than the Earth. And 9 to 10, actually, because it's kind of on an elliptical orbit. And then Titan's atmosphere absorbs quite a bit of the sunlight that hits the top of the atmosphere. But even if you assume that only about 10% of the sunlight that makes it to Titan hits the surface, you can calculate how much, it's all about the square, you know, the area covered by the photovoltaic cells and how efficient they are. And so presumably if you cover, you know, some percentage of the surface of Titan with photovoltaic cells, you can produce plenty of power that way. So there's lots of options for energy, and even for making oxygen, because there's so much water there.
Yeah. Has there been any discussions or ideas at all about heat, you know, how to relatively quickly heat up the surface of the planet, or is that total science fiction?
Say it again, how relatively quickly what?
About to heat the surface of a planet, how to make it warmer. That's kind of terraforming in a way. But.
Right, kind of terraforming. So obviously people have talked about that for Mars. One could think about that for Titan. Personally, I've always kind of advocated for adapting to an environment rather than adapting the environment to us. I think humans are smart enough to do that. I kind of think we've adapted this planet a little too much. But yeah, there are ways to do that. I think in our book, we wrote about some of the ideas that, for instance, Elon Musk has at Mars about how to do terraforming there. And it sounds to me like everything's just going to take tens of thousands of years to happen. And so I don't really think that's the time scale that we're trying to talk about for, you know, making humans a multiplanetary species. I think we'd like to get things going far faster than that if we want to do that. Yeah. By the way, I want to go back to the previous question because I think I got off track. I was talking about the temperature and how that is a challenge at Titan and how we can address it. But the other big challenge, of course, is the fact that it is far away. And so there's no popping back and forth between Earth and Titan to get supplies or whatever. And that's actually one of the attractive things about Titan, because it does have so many resources that if you really want to create a permanent and self-sustaining settlement, Titan is a good place to do it. But first you have to get out there, and your humans have to survive the trip. And right now, using chemical propulsion, you know, it took Cassini 7 years to get there. And so that's not really that great of an option for sending humans out there.
Yeah, and
so that to me is the real issue, that we need to come up with a faster propulsion, a faster realistic way of getting humans out there.
Yeah, and didn't, correct me if I'm wrong, but didn't Cassini do, when they send these things out, don't they do some gravity assists?
Yeah.
So that if you're sending a rocket with humans on it, you would probably take longer.
Well, hopefully you would skip the whole gravity assist thing and you just go straight out there. But again, you need, I mean, the reason that Cassini didn't do that is because to go straight out there, you need to carry, you even more propellant, because the whole idea of doing the inner solar system gravity assist is to save on propellant and getting enough energy from those gravity assists to propel you out there. So, you know, that adds time. So if you're sending humans out there, you'd probably want to come up with some way of skipping that whole part of the tour and just going straight out there. But again, it costs propellant and it still costs time to get out to 9 or 10 AU.
Yeah. Now, what was the one most astounding finding from the Cassini probe that you found the most interesting or exciting?
Are you asking me what is my?
Yeah, I mean, it mapped out all of these, but which one of these, let's say, surprised you the most or excited you the most?
About Titan or anything on the Cassini?
Titan.
Oh, the lakes, I think. The lakes, that was awesome, that they're really there, and just how Earth-like it really makes Titan seem even more Earth-like than we kind of were already getting the sense that it was. But just to know that there's this place, you know, out orbiting Saturn that really looks like the Earth. And a lot of people compare it to early Earth, you know, because there was a point in Earth's evolution where before it had O2 in the atmosphere, and so it had a lot of prebiotic chemistry going on, which might be what is happening on Titan. And so it's not unreasonable to call Titan very similar to early Earth, and in a lot of ways to current day Earth too, because of the geology.
Yeah. No, I know you've done a lot of work also on the other moons of Jupiter, I think, and the other moons of Saturn. Can you tell us about, are there any candidates among those that could be useful for
in terms of human settlements?
Yeah.
Well, Titan is my favorite, and mainly, of course, because of the atmosphere. But you can consider the other moons too, whether they're going to be good for humans. So let's talk about the Jovian satellites, the Galilean satellites. There's Io, Europa, Ganymede, and Callisto. These are the 4 Galilean satellites. And named after Galileo, because he discovered them in about 1610.
These are around Jupiter, correct?
They're around Jupiter. And all these moons are roughly Earth moon size. So they're, you know, pretty decent sized moons. Europa is the smallest of them. It's a little smaller than Earth's moon. And Ganymede is actually the biggest moon in the solar system. It's a little bigger than Earth's moon. But
Ganymede has no atmosphere, right? It looks like our moon, actually.
It looks a lot like our moon, but it's quite different. The reason it looks like our moon is because of all the craters. It's actually mainly water ice. Matter of fact, even though it's a little bigger than our moon, in radius, it's about 1.5 times the Earth's moon radius, but the gravity is only about 15% of Earth's gravity. Whereas, you know, the moon has a little more than that. And that's because Ganymede is mainly water ice. It has some rock in the center, in its core, but it's quite a bit less dense than the moon, which means that the gravity is a little lower. But all the craters, I mean, ice acts like a rock out at those cold temperatures. It's 120 Kelvin or something. And so impactors come in and just make craters, a lot like we see on Earth's rocky moon. And the ice gets dirty, probably from a lot of the impactor material coming in, a lot of like carbonaceous stuff, probably darkening the surface. But interestingly about Ganymede, it does not have much of an atmosphere. It's just a very scant atmosphere that's probably mostly kind of sputter produced. So charged particles from Jupiter's strong magnetic field hitting the surface and sputtering water ice, and it makes it up into the atmosphere. It's very tenuous, and probably, you know, if that magnetosphere were to somehow turn off, the atmosphere would not last very long. But the interesting thing about Ganymede is that, you know, it's got that rocky core. We know from the density, it's got the rocky core, and it actually is the only moon in the solar system that has its own magnetosphere. So there must be some movement of material in that core to generate a magnetosphere. And so just like the Earth, just like, you know, it's different in ways, but the Earth, Ganymede, has a magnetic field that produces aurora. So when those charged particles come in and hit what is there of the atmosphere, the gases in the atmosphere, they actually illuminate. The gases get excited and light up, and they light up along these field lines because those charged particles are sort of transported along the field lines, just like with the Earth's aurora or northern lights. So that's what makes Ganymede unique. But Ganymede, Europa has a very thin atmosphere. Callisto has a very thin atmosphere. These are all icy moons. And we really would not consider sending humans there because that radiation environment at Jupiter is so intense that you know, we even worry about sending spacecraft to Jupiter or to Europa because the radiation environment just hammers the equipment, the electronics, not to mention, you know, human tissue. So not good places for humans, although very interesting nevertheless. And Io, I didn't mention, it's not an icy moon. Io is the most volcanically active body in the solar system. And matter of fact, probably used to have water ice, but it probably all burned off a long time ago. And now it's just a bunch of rocky material that's just very volcanic, thanks to all those tidal interactions with Jupiter and the other moons.
Yeah, it looks like a yellow, rotten, it's a very curious look for a moon.
I know, it looks like a pizza, doesn't it?
Yeah.
It's all volcanic material.
Mm-hmm. Does Titan have a magnetosphere?
Titan does not have a magnetosphere.
So what does that mean exactly? I know the magnetosphere protects against some radiation also.
Right.
Probably it's compensated for by the thick atmosphere. Are there any other implications?
It just tells us about what must be happening in the interior and how much metal and rocky material must be in the middle, and what its sort of interior structure must be like. We know that Titan has a subsurface ocean. Okay, like all of these moons that I'm talking about, except Io, they all have subsurface oceans. And that means that, again, they're mainly water ice, but they've got enough heat generated in the interior that there is a layer of ice. Sorry, there's a layer of water in the interior that is kept liquid. And so there's actually a liquid ocean in all of these moons. And we know this from Titan because with Cassini, we were there for long enough. And we know that Titan is on just a slightly elliptical orbit around Saturn. And that slight difference in distance means a slight difference in gravitational pull from the planet at the different points around the orbit. And what we were able to actually observe was a very slight change in shape of Titan itself, which can really only be due to kind of a plastic or elastic type of movement that is the result, most likely, of a layer of liquid in the probably quite a few tens of kilometers underneath an icy layer. But for instance, back to Europa in the Jovian system, it was the first world that we knew of that has a subsurface ocean. And that was detected by magnetospheric magnetometer measurements from the Galileo spacecraft. And there, at Jupiter, it's a little easier to detect a subsurface ocean because its magnetic field, Jupiter's magnetic field, is tilted by about 10 degrees from the spin axis. And so it produces a wobble in the magnetic field as it goes around. As each of the moons go around, they're going through this wobbly magnetic field. And the magnetometer on Galileo back in the 90s, I think the paper came out in about 1996 or 7. The magnetometer team put out a paper saying, we think that there's an ocean in the subsurface of Europa. And we know this because there is something that is perturbing the magnetic field lines of Jupiter at Europa's orbit. And it's most consistent with a conducting subsurface layer, like a salty ocean, producing an induced magnetic field at Europa itself. So Europa, unlike Ganymede, has an inherent magnetic field. It's just produced inside its core. But Europa actually has an induced magnetic field. It's induced by the interaction between its conducting salty ocean layer and Jupiter's moving magnetic field. It moves by it and makes an induced magnetic field.
Yeah. Do we know if that the underground ocean in Europa is actually H2O for sure, rather than another type of liquid?
H2O is the most plausible thing because, again, there's so much H2O out there, and we know that the densities of these moons is most consistent with H2O plus some amount of rock. We know that there's H2O on the surface because we can see the spectral signatures. So it is most likely just basically melted H2O in those subsurface oceans. Yeah.
Okay. And yeah, can you do, so I was going to ask you to do a comparison between Mars and Titan, but are there any advantages to Mars as a place for permanent human settlement rather than Titan, other than the physical proximity to Earth?
Right. That's the number one thing in my mind is it's relatively easy to get to Mars. So that's the reason that Mars should be first on our list. Mars or the moon should be first on our list for when we send humans out of low Earth orbit. That's where we should go. Probably the moon first and then Mars. And for a permanent settlement though, if you want to set it up on Mars, you can do that. But you just have to transfer out your crew very frequently because anybody who stays there for a long time is just going to get cancer and brain damage before very long at all. Unless they live underground, that's a possibility. To me, it doesn't sound like that attractive of an idea. I think if you're going to go to another planet, you may as well live above ground and be able to go out and walk around and so forth. And do your science experiments. That's the whole reason to go, right? So the proximity, right now though, for NASA's cancer risk guidelines limit humans to about 200 days outside of low Earth orbit. But a Mars mission is probably going to take a good 3 times that. So something needs to be adjusted there to make that a reality. But on Mars, there's a very thin atmosphere. It's only about 0.5% of a bar surface Earth atmospheric pressure, and it's mainly CO2 in the atmosphere. There's water, ice in the subsurface, and some in the polar caps too. There was even the recent discovery of a likely lake, maybe like a mile below the South Polar Cap. That was measured by the radar on ESA's Mars Express mission. So maybe there's probably plenty of water to access to, if you want to make oxygen, if you want to make liquid water to drink and live on and so forth. So there are some resources there. And there's, talk about using CO2 as a resource for making fuel and so forth. So it's not completely out of the question. But
yeah, they're talking about CO2 from the atmosphere with water that they can extract to make fuel.
Yes. Yeah.
Which on Titan you can just take away from the lake.
Yeah.
Yeah. Right.
Yeah, Titan makes everything a lot easier, I think. But so it's not out of the question for Mars. But again, because there's no protection there, you can't live there for very long, or you have to really think about how you can have humans live there for very long. I've heard people talking about, terraforming to make an atmosphere I've even heard about people talking about making a magnetosphere again at Mars, because of course it used to have a magnetosphere, but it's lost. And if you did that, then you'd have natural shielding again. It wouldn't be very natural. But, you know, again, we're talking about really big engineering projects that are probably going to take a long time and aren't really that feasible.
Yeah, so right now it's beyond our technological abilities
Yeah.
to do that. Yeah. And like just with such a thin, almost negligible atmosphere, how do they get winds and dust devils and you get these big storms that we see that cover the whole, how do you get that when there's no atmosphere?
No, it is 0.6% of a bar of atmosphere, and it is enough to make dust devils and wind, you know, global dust storms and everything. It's pretty incredible. On the Martian, evidently that windstorm was a little, you know, more than realistic.
Yeah. People like to have their imaginations on
embellish, yeah. But you know, it is a thin atmosphere, but it's just not enough to do very much shielding against radiation. Now, the main radiation that I'm concerned about is the galactic cosmic rays, because those are the most energetic, and they're you know, not predictable solar storms and so forth. They're just kind of constant. And from every which way. So shielding from them is the hardest, and that thin Mars atmosphere will not shield against. You know, it's often said that Mars has enough of an atmosphere to make it a big problem. You know, in terms of getting, you know, spacecraft, including humans, down to the surface. If you're trying to land on the moon, you know, its lack of an atmosphere almost makes things a little easier. But Mars, you've got enough of an atmosphere that you really have to consider it, because it can really screw things up.
Yeah. Now, other than Titan and Mars that we just mentioned, are there any other planets on the solar system that potentially could be used, if not for realistically for permanent human settlements, maybe for bases, or probably not, eh?
Well, the other crazy idea is Venus.
But I mean, they were talking about Venus being, the atmosphere is so thick and it's so hellish that they'd go in the sky and be in the atmosphere.
You need to go in the sky.
How realistic is that? Yeah.
I know. So it definitely would not be Earth-like, because you'd be living in like habitats that are floating, you know, but it would be there, you know, you'd be at a level in the atmosphere where you have 1 bar of pressure. So that could be kind of nice. But again, not Earth-like at all. But
have you ever wondered in your fantasies whether you could take some of the atmosphere from Venus and put it on Mars and just redistribute things?
Yeah, I'm sure people have tried to think about that.
I'm sure that'd be your request if you met God. That's what
well, you'd have to turn back the clock to when Mars used to have a magnetosphere and an atmosphere, you know, and water was flowing on the surface, you know, then it must have been much more Earth-like.
Yeah. Now there is, do you think there was a planet around Mars before that's now gone? That's why there's the asteroid belt there?
I think the asteroid belt is mainly not so much a former planet, but just kind of leftover planet-making material. Actually, it has a couple of dwarf planets in it. Like Ceres is the largest asteroid, and it's considered a dwarf planet because it's, you know, big enough to be round, and it's just not a full-on planet yet because it's in the asteroid belt. But the Mars, you know, the asteroid belt is probably just, you know, material that is kind of, like I said, left over from the whole planet making formation. There could be clues in the asteroid belt to early solar system processes, because there's ideas that, you know, Neptune and Jupiter moved around and moved because of their influential gravity fields, a lot of the small bodies away into the asteroid belt and into the Kuiper belt and maybe into those Trojan asteroid populations that are out at Jupiter's orbit. But a lot of the material in the asteroid belt now is in stable positions. some of it can get kicked out by gravitational perturbations and become near-Earth asteroids. But a lot of it is pretty stable. And of course, the Jovian Trojan asteroids are in, stable Lagrangian points at Jupiter's orbit, and they're very stable because otherwise they would be kicked out to who knows where by Jupiter's gravity.
You think some of this volatility that you were talking about might explain Uranus's unusual tilt?
Right. Some big dramatic event in the early solar system must have, completely tilted Uranus over on its side, basically. Thinking about going back in time and seeing what must have been happening back then, that would have been interesting to witness.
Yeah, great. Yeah, and lastly, I just wanted to go over your book. I know you co-authored with someone who's not a scientist, but a writer.
Writer.
And yeah, there's a lot of things in there that are not necessarily science. It's talking about social structure and ethics issues. And was that kind of his, how did he write some chapters and you wrote some, or did you both collaborate on everything, or whose idea was it to include what?
Well, it was both of our ideas to include basically all of the topics, but we wanted to really cover a lot of the issues that go into thinking about sending humans to another planet. And one of the main things that we wanted to make it as realistic as possible, right? And so one of the main things we wanted to think about is why we would ever do this, really, why do we ever want to set up a human settlement somewhere else?
What's your answer to that? If somebody asks you,
well,
one-liner, yeah.
For the book, we came up with a scenario where we need to, usually, and we talked a lot, and this was fun to write and fun to talk with Charles about and think about. But, we talked about, colonization on the Earth in history and why people ever moved around, to the New World and from places, and why they would make these big moves. And, when you think about it, mainly it's either to get away from something bad, like a bad monarchy, or because you're getting something you're making some money, or you have a new business deal, and you're somehow gonna, set up a new business in this new place. But there has to be either a benefit or something bad that you're getting away from. And, that we know of right now, sending humans and even some spacecraft to different locations in the solar system is not a big money-making generator. You're not making money. There's not a lot of resources or wealth to be obtained. But the important thing to do it, the important reason to do it is to learn, right? And to learn about our solar system and our surroundings and how we got here. So we decided to adapt the approach that, well, maybe humans would want to create a permanent settlement elsewhere in the solar system because they're trying to get away from something. And maybe the situation on Earth has gotten so bad, probably it's not too out of the realm of possibility that global warming could get so bad that conditions on Earth would make us really want to create a settlement someplace else, and people would want to leave.
Don't you almost have to kind of do that before it gets to that point where it's so bad? Because you need a lead time of.
Yep. Right? So you need a lead time. And so some people are talking about doing that now. Like, we are going to want to become a multiplanetary species, or we are going to have to be. And so we need to start thinking about this now, for sure. But also, of course, another point of the book was to think, well, maybe if we don't let things get to the point where we need to leave, and we take care of our own home planet, then it won't be a situation where we have to leave. It'll really be because we want to go out there and learn more about the solar system and where we came from.
Great, awesome. Yeah, well, thank you very much. This was really amazing. Anything else you wanted to add or?
I don't think so. It was fun talking to you, and I appreciate your interest in the book.
Great, perfect. Well, thank you very much.
Okay, bye-bye.